Good afternoon. The title, as you can see, is rather long, and so you can ignore the title for the time being. We will get there in a few minutes, what it means. So this is the plan for the talk today. And so let's start with something all of you must be familiar with, and all of you must recognize this graph, what kind of a graph this is, right? Yeah, it's a split graph. And what's a split graph? We can partition its vertices into two parts so that one part induces a clique and the other part is an independent set. So once we have a graph class, well, there are algorithmic questions that we would like to ask, and the two natural questions that we often ask are, one is the recognition problem. If you're given a graph, does this graph belong to this class? And the other is the deletion problem, which is you're given a graph and an integer k. The question is, can you delete k vertices from this graph so that the remaining graph belongs to this class? So in the case of split graphs, all of you must know that the recognition problem is polynomial time solvable and the deletion problem is NP hard but fixed parameter tractable, parameterized by k. Okay, so I presume all of you know fixed parameter tractable algorithms. So when I signed up for this, I only expected the IMSC crowd, and so give me a second. If our algorithm runs in time some f of k n power c, we say that this is fixed parameter tractable. The problem is fixed parameter tractable, okay? So now we try to generalize the problem a little. We do not allow all split partitions, which is we do not allow all partitions into clique and independent set. We impose some more conditions. So what are those conditions? Every vertex comes with a list. What is a list? For vertex v, it has a list L of v, which is a subset of 1, 2. And what does it say? It says that a vertex can go to part vi only if I is there on its list. Okay? So we define so we start with a graph and a list function L. We say that v1, v2 is a partition that respects this list L if 1, v1, v2 has to be a partition, 2, v1 must induce a clique, 3, v2 must be an independent set, the same as for split partition, but now there is one more additional constraint, which is the list constraint. That is, the vertex v can go to part vi only if I is there on its list. Okay? And again we get two computational questions. One is the recognition problem and the other is the deletion problem. And it is not very difficult to see that, I mean, assuming the result for the recognition and deletion problem without lists, it's not very difficult to see that the recognition problem here would be polynomial time solvable and the deletion problem would be NP hard and FPT. See, if you have a split graph, how many different split partitions can it have? Only polynomially many, right? So you have a clique and an independent set. How many other such partitions can be there? At most one vertex from the clique side can go to the independent set part, and at most one vertex from the independent set can come to this side. So once you have a split partition, which you know how to check, these problems will be polynomial time and FPT respectively. So the list problem actually generalizes the corresponding problem without list. We can set up L of v equals 1, 2 for every vertex and we get our original problem back. Okay, so now is the interesting part. Now we come to what we actually want to talk about. So a split partition, it can be characterized using this matrix. So what do these entries stand for? So first of all, the matrix has order 2, which means we are looking for a partition of the vertex set into two parts. Okay, and look at the entry M11, it's equal to 1. That means the first part V1 must induce a clique, and the entry M22 equals 0, which means the second part V2 must be an independent set. And the off diagonal entries, you can see they are stars, which means we don't really care about the adjacency between V1 and V2. They can be arbitrary. Okay. So the next thing is, there is nothing special about this particular matrix and split partitions. We can look at any matrix, any symmetric matrix with entries 1, 0 and star, and that will define a partition. So that is what is called an M partition, where M is a matrix over 0, 1 and star. So for an L cross L matrix, we are looking for a partition into L many parts. It should be a partition, and the ijth entry equals 1 means Vi and Vj, parts Vi and Vj should be completely adjacent. There should be all the possible edges between them. Okay, and if I equals j, that means the part Vi must be a clique. Okay, and similarly Mij equals 0 means these two parts should be completely non-adjacent. There should not be any edge between them. And again, if I equals j, the part Vi should be an independent set. And if it's star, then we don't care about the adjacencies. So let's look at some matrices. So this matrix M1 we already saw. It corresponds to the split partition. What about M2? There are two parts. So M2 has order 2, which means we are looking for a partition into two parts. The diagonal entries you can see are zeros, which means both the parts must be independent sets, and the off diagonal entries, they are stars, which means we don't care about the adjacency between the parts. So M2 characterizes what? Bipartite graphs. And similarly M3 characterizes what? Three colorable graphs, right? Now again we are gonna impose the, so we saw what we did. We saw an M partition. Now we are gonna impose the list constraint on M partitions also. Okay. So again we have a graph. Now we have a list function also. And sorry. Okay, I came too far. Yes. So now we have all the constraints that are there for an M partition, plus we have an additional constraint, which is what? If a vertex must go to a part, say Vi, then I should belong to the list of that vertex. So this is what we call a list M partition. Okay. And so again we come to our algorithmic questions. One is the recognition problem, where the input consists of a graph and a list function, and the question is, does this graph have a list partition that respects the given list? The other is the vertex deletion problem, where we have graph, list function and an integer k, and the question is, can you delete k vertices so that the remaining graph has a partition of the required type? So this is going to be our problem, the deletion problem. And again, list problems generalize the corresponding non-list problems. And so what is our goal? Our goal is to look at all matrices of all small matrices of order up to 4, and look at the complexity of the corresponding M partition vertex deletion problem. Okay. And our parameter is going to be k, the solution size. So these are our results. The first one is for matrices of order at most 3, And we show that then the list M-partition deletion problem must be one of these 4 types. It should be either polynomial time solvable, or it should be NP-hard and FPT, or it's para-NP-hard, or it should be solvable in this sort of a running time. Okay? And and for matrices of order 4, we did not manage to show results for all 4 cross 4 matrices. We only looked at matrices that do not have stars on the diagonal. So all diagonal entries are either zeros or ones. Okay? So we showed that in this case, the problem, the list M-partition vertex deletion problem, must be either para-NP-hard, or it should be NP-hard and FPT. So this will be para-NP-hard if it contains the 3 coloring matrix or its complement. So what is the complement of a matrix? We replace all zeros with ones and all ones with zeros. Okay? So as you know, the 3 coloring problem itself is NP-hard. So any partition that encompasses a 3 coloring is going to be NP-hard even for k equals 0. Okay? So these are our results. And okay, so this is that put in a table form. So one more thing. So we already saw a complement of a matrix. So if a graph admits an M partition, if and only if the complement of the graph admits a complement of M partition, right? So M bar is the complement of M. So G has M partition if and only if G bar has M partition. So matrices here are written up to complement, and also, you know, if 2 matrices define the same partition up to a reindexing of parts. For instance, these 2 matrices define the same partition, right? So then they are considered the same. So matrices are written up to complement and this sort of equivalence. So in this case, so for all these matrices here, the problem is polynomial time solvable. These 2 matrices, they are going to be para-NP-hard. All other matrices are FPT. So for this one matrix, we do not know whether it's polytime or NP-hard, but we show an FPT algorithm. And for this matrix, we don't know whether it's FPT or W-hard, but we give this sort of an algorithm, some f of k n power log n kind of algorithm. And for 4 cross 4 matrices, we only look at matrices without stars on the diagonal, and if it contains this matrix or its complement as a submatrix, it's para-NP-hard, otherwise FPT. Okay? And now, why are we doing all this? One thing, we saw that these problems generalize as a number of recognition problems and deletion problems and all that. So that is one motivation. The other motivation, of course, came from the work of our guest, Professor Hell. So he and his colleagues studied the list M-partition recognition problem and proved a number of results. One was the classification of small matrices, and they showed that for 3 cross 3 matrices, the recognition problem would be NP-hard if it contains 3 coloring, this matrix, or this matrix as a 3 cross 3. So if it is this or this, then it's NP-hard, otherwise polynomial time solvable. And for 4 cross 4 matrices, it's going to be either NP-hard or quasi-polynomial time solvable. And Quasi-polynomial time, of course, is an upper bound. Many of them are actually polynomial time solvable, and actually they are polynomial time if there are no stars on the diagonal and does not contain this or this as a submatrix. So this is for 4 cross 4 matrices. Okay, and this was in 1999. Then there was something else called sharp list M-partition, where the goal is to count the number of list M-partitions of a given graph, and this has been shown to be either FP or sharp P complete in 2015. The one other is actually a deletion problem. It's the list H homomorphism deletion problem. So what is list H homomorphism deletion? Well, list H homomorphism recognition problem would be, we are given two graphs G and H, list function, and the problem is there a homomorphism from G to H? In deletion problem, we also have an additional input, an integer k, and the problem is, can you delete k vertices from G so that there is a homomorphism from the remaining graph to H, with that respects the list L, of course. So this has been shown to be FPT when parameterized by k and size of H, when H is a P6 C6 free bipartite graph. This was in 2013. Okay, so again, recall our problem. We have a lot of time. I think I'm going too fast. So again, this is our problem. Graph, list function, integer, delete k vertices so that the resulting graph has an M-partition that respects the list L. Okay. So as we saw, our algorithms are of different types: polynomial time, FPT, 2 power k, n log n, n power log n, para-NP-hard, and all that. So we had to use a number of different techniques, and some of these and a combination of some of these techniques to get our results. Some of them involve reducing our problem to a minimum separator problem, and one of the most useful techniques we were able to use was to reduce the problem to a problem called variable deletion almost 2SAT. So all of you know what the 2SAT problem is. You are given a 2CNF formula and the question is this formula satisfiable? In variable deletion 2SAT, the question is, you are given a formula and an integer k. The question is, can you delete k variables from the formula so that the remaining formula will be satisfiable? And what do we mean by delete a variable from a formula? We will delete all clauses containing that formula or its negation. Okay. So, and this problem, variable deletion almost 2SAT, is known to be FPT. And so one of our techniques is to reduce our problem to some polynomially many instances of this problem, variable deletion almost 2SAT, and use that known algorithm for that problem to solve this. Then there is something called important separators that we use. We will come to that in a minute. And then there is something called separating families. And those of you who have seen a FPT algorithm for split vertex deletion using separating families would recognize this object. So it's basically a collection of vertex subsets, usually of n power log n size, with the following property. If you are given a clique and an independent set in the graph, any clique and any independent set, there will be a set in the family that contains the clique and completely excludes the independent set. Okay, so these objects, the cliques and independent set, so similar separating families exist for separating other objects as well. It doesn't have to be cliques and independent sets, but similar objects also. So that is what a separating family is. And then iterative compression, it's a standard textbook FPT technique now. Basically, we start with a bigger solution and try to compress it into a smaller solution. So these are some of the techniques that we use. Okay, so let's see two very easy examples of our results. So let's look at this matrix. It's a 3 cross 3 matrix. So if we want to partition the graph into 3 parts, the diagonal entries are all stars. So we don't care about the adjacency inside each part. And also look at the third row, M13 and M23. The entries M13 and M23, they are also stars. That means we don't care about the adjacency between part 3 and part 1 and part 3 and part 2. But the entry M12 is 0, which means there should not be any edge between V1 and V2. Okay, so we look for this sort of a partition. And again, what is our goal? We want to delete k vertices so that the remaining graph has this sort of a partition. So first let's define these 3 sets. So what is X? X is the set of all vertices that must go to V1. So L of V equals 1. Therefore, the vertex should go to V1 or it should be deleted. Similarly, Y, it has only 2 on its list. So every vertex in Y should either go to V2 or it should be deleted. And Z, we look at all vertices that contain 3 on its list. Okay. So first observation is there is no need to delete any vertex that belongs to Z. Why? We can put that vertex in V3. First of all, V3, since we don't care about adjacency within V3, there is no problem. Also, we don't care about these 2 adjacencies. So as long as a vertex has 3 on its list, we can safely put it in V3. And then what happens? So all the remaining vertices should either go to V1 or V2 or be deleted. Note that none of the vertices outside Z, no vertex in G minus Z can go to V3. And so we can forget that V3 even exists now. And what is the problem now? The problem is we just want to separate V1 and V2, or in other words, we want to separate X and Y. X can go only here, Y can go only here. So we only want to separate X and Y. So the problem reduces to, finding a minimum XY separator in G minus Z, which you can do in polynomial time. Okay, now let's look at something I mentioned earlier. So I told you we can reduce this to this variable deletion almost 2 sat. And how do we do that? We can actually reduce the recognition problem to 2 sat. So suppose this is our matrix. Okay, so this is the split matrix. And giving an example, for every vertex we introduce a variable xv and we attribute this meaning. Xv gets 1 means we must go to part 1, xv gets 0 means we must go to v2, and v1 we want it to be a clique, v2 an independent set. First of all, let's look at these 2 constraints. So these are the clauses that we are going to introduce. So if L of v equals 1, then this vertex should go to v1. So we introduce this clause, a single literal clause, and for 0 we introduce this. And now for every pair of vertices u and v where there is no edge between u and v, at most one of them can go to the clique part, right? So we introduce this sort of a a clause, and so this means what? Xu bar or xv bar, so at least one of them should get 0. The variable should get 0 assignment, right? Similarly, for every edge, we introduce this sort of a clause, and the resulting two-set formula would be equivalent to checking whether the graph has a list partition. So this reduction is quite, so this reduction again dates back to Professor Hell's paper. So this reduction is actually quite nice. For every vertex, we have exactly one variable. And this is why, okay, let me just, so, the corresponding deletion problems also correspond very nicely. The deletion problem for the list matrix partition deletion problem, it's an S instance if and only if the variable deletion almost 2-sat for this formula would be satisfiable. So here we looked at a 2 cross 2 matrix. The thing is that the matrix doesn't have to be 2 cross 2, but as long as the list of every vertex is at most 2, we can still make this work. Okay? So we get that the recognition problem then would be equivalent to solving a 2-sat problem, which is polynomial time solvable, and the deletion problem would be FPT, because the deletion problem then would be variable deletion almost 2-sat, which is FPT, when the list of every vertex is of size at most 2. Matrix M could be large. Okay, so keep this in mind. We will see one more example. So let's look at this matrix. So the first 2 diagonal entries, they are both 0, which means the first 2 parts, they should be independent sets, and the third diagonal entry is a star, so we don't care about the adjacency within this part. And now what? Okay, 1, 2 is a star, so we don't care about this adjacency, but 1, 3 and 2, 3 are stars, so there should not be any edge between this and this, or this and this. Okay, so let's see how we solve this problem. So again, we define 2 sets. X contains all those vertices that has only 3 on its list. So every vertex in X must go to V3 or be deleted. And Y should belong to one of these 2 parts or be deleted. So suppose this is the optimum solution that we are looking for, okay? Suppose our instance is a yes instance and there is a solution of size at most k, and this is the solution S that we are looking for. So first observation is that S must contain an XY separator, right? Because there are no edges between this part and these 2, and everything here goes here and everything in Y goes here, our solution should necessarily contain a separator, an XY separator. But which XY separator? We don't know. And there could be n power k many XY separators of size at most k. So we can't simply enumerate them and check if this is the separator that we are looking for. So this is how the picture looks like. So this is X should go to V3, the part above, and Y should go to the part below, V1 or V2. And our solution, suppose our solution is S, and S prime is an XY separator that is sitting inside our solution. Let's say that separator looks like this, okay? The thing is that As you can see, there is another xy separator, let's call it S double prime, that is a little further away from x than S prime is. So what are the good things about S prime, or the properties that S double prime has but S prime doesn't have? One thing, now there are more vertices that are reachable from x. If we delete S double prime, more vertices are reachable from x than if we delete S prime. Similarly, the vertices that are reachable from y, if you look at them, the smaller number of vertices are reachable from y now than if we delete S prime. So and we can't go any further. We can't go any further without increasing the size of the separator. Note that S prime and S double prime, they have the same size, but if we want to find a separator that is still further away from x, we are going to have to increase the size of the separator. So S prime is a really good kind of separator, and such separators do have a name. They are called important separators. Important separators were introduced by Daniel Marks, I think in 2006 or so, and it has proved to be a very useful tool. It has been successfully used for solving problems like multi-way cut, directed feedback offset, etc., etc. And the good thing about important separators is that there are only FPT many, some f of k many important separators of size at most k, and we can enumerate them also. So this again, the things that I mentioned. So reachable from y, if we delete S double prime, that is the set of vertices that are reachable from y, if we delete S double prime, they are smaller than the set of vertices that are reachable from y if we delete S prime. That is one thing. The other thing is that if a vertex is not reachable from y, then it must have 3 on its list. So what was y? Y was all vertices such that L of p is contained in 1 or 2. So this was our y. So if a vertex is not reachable from y, I'm talking about after deleting our solution, okay, then 3 must be there on its list. So we can safely place that vertex in V3. So what does this mean? This means that if we have a solution, then what can we do? That solution, we said that solution must contain a separator. So what do? We take out that separator and replace it with this sort of a separator. That is, we call this, so if this happens, we say that S double prime dominates S prime. Okay, so we replace S prime with S double prime, and what we get is still a solution. Okay, so again, recall this fact. We said that if the list of every vertex is of size at most 2, then the problem is FPT. And these are our sets x and y. So our algorithm is going to be this. What do we do? For each important separator S double prime, we will check if this is the important separator, if this is the separator that is sitting inside our solution. So that is what is happening here. What do? So we want this separator to separate x and y, and we want to delete some more vertices. So what happens if we delete this? So we deleted S double prime. So we separated V3 from V1 and V2 with S double prime. Now we want to delete more vertices so that the constraints over this part is also satisfied. But now we can forget V3 altogether, right? Because every vertex that is not reachable from y now has 3 on its list and we place it in V3. Every other vertex must belong to V1 or V2 or should be deleted. So what can we do? We remove, so we look at all vertices that are reachable from Y. We remove 3 from its list. Now every list has size at most 2 and we set the budget appropriately, and now that every list has size at most 2, we can solve the problem in FPT time. So if this instance is a yes instance, we will return that. Our original instance is a yes instance. And the important thing is we have only some f of k many important separators that we have to try out before we can conclude whether this is a yes or no instance. So this is a fairly standard technique that is always used in problems like in cut problems, in separator problems. Okay, so yeah, that's about it. So there are a few more things that we would like to do. One is to complete the classification. For 4x4 matrices, we only looked at matrices that do not have stars on the diagonal. So we would like to complete that, all 4x4 matrices. The other thing is, for this one matrix, we said we did not know whether it was P or NP hard, but we have an FPT algorithm, so we would like to determine that. And for this matrix, so this matrix is what is called a stable cut set partition. So as you can see, these are 2 stars, so we don't care about their adjacencies, but here, sorry, this is a clique cut set, sorry. So here this is a 1, so the part V3 must be a clique. And also note that we don't care about adjacencies between V1 and V3 and V2 and V3, but between V1 and V2 there are no edges. So if we remove V3, so V3 is like a cut set between V1 and V2. Okay, so that is why this is called a clique cut set problem. And for this problem we have some 2 power order k poly n algorithm, but we don't know whether it's FPT or W hard, and we would like to determine that also. The other thing, is we only looked at FPT algorithms. We don't know anything about kernels for these problems, so do a similar classification study for the kernelization complexity of these problems. Yeah, that's all. Sure.
When you talked about 2 problems, one was the recognition and the other one was the remove. But now you are just talking about the second problem.
Yes, yes.
Not about recognition.
This is not about recognition.
And I wanted to add that the problems that we only were able to prove quasi-polynomially at that time in 99 have since all been
Of course,
polynomial.
yeah.
So I think maybe, for example, the deletion problem for the stubborn problem might be quite hard. Have you tried to do the deletion problem of that matrix? It's a 4x4 matrix. There's some asterisks on the diagonal.
No, we did not.
Whether you can actually easily complain.
So FPT algorithms, I think, should be possible because iterative compression is quite a powerful technique, and we were able to use iterative compression for many 4x4 matrices. So FPT algorithm I'm not that worried about, but showing NP hardness when there are all stars on the diagonal would be a big issue.
One other thing I wanted to add was that for list split partition, in addition to this reduction to 2-sat, there is a nice one-pass algorithm. I don't know if you have seen it. I think maybe in our book on homomorphisms.
Okay.
Which basically you order the vertices as a chordograph. First all independent sets, then all the clique.
Yes.
And then do a one-pass algorithm looking at the lists and deciding.
Yeah.
Kind of neat.
Okay.
I will send you a reference.
Thank you.